Hello everybody. Uh, Welcome to week 5, um, network structures and cloud computing. And today we're going to talk about number systems and networking basics. I think that based on the prerequisites for the course, you're not supposed to be a computer science, but I guess that it will be a valuable um, topic for people that have a fairly have less context in those areas, and for those who did some computer science, I think that it will you can skip this this lecture. So one of the objectives that we are going to have for understanding some of the number systems concept is to recognize and be able to demonstrate how different types of information are represented as numbers, binary, decimal, and octal bases. We're going to focus mainly on base 2 and base 8, which is octal, and then base 10. Want to identify and be able to list and describe the largest and smallest signed and unsigned numbers. This is basically important when you have a set of a subnet, a subnetwork that you want with a range of IPs, and you want to assess how many IPs are available for you. And one of the real life example that one can use it is that when you launch a group of VMs in the cloud, you have the option to create a subnet for it, and the size of the subnet is is a factor of of such calculations. And this is a few of the motivation of why we learn, and as I mentioned, this is one of the reasons of how what net mask should I use if I use a network with up to 20 machines. Yeah, you can go through this, and we're gonna look for it. We're gonna look into it a little bit more as we go. This is a quick overview of how you describe 10. It's basically a positional system, a 10 positional system, uh, and the example here is a self-explanatory. If you want to describe 1, it's basically 10 to the 0. If you want to describe 10, it's 10 to the 1. If you want to explain, to describe 100, it's 10 to the 2, 10 to the 2 square, and a number system and base 2, which is binary, is pretty similar, but it's a base 2 positional system. So if you want to describe the number 100101100, it's basically you count the positions of the ones, and you calculate the and you calculated the numbers of 1. So in our example is that it's 2 to the 8 plus 2 to the 3 plus 2 to the 2, and then you get 300. This is how you basically convert a number from base 2 to base 10. And this is just a few known sizes: kilobyte, megabyte, gigabyte, and terabyte. So kilobyte, it's 2 to the 10th, and megabyte, it's 2 to 20th, gigabyte, terabyte, and this is even a broader scale of memory management terms. Essentially, 1 bit is 1 symbol, and then 1 byte is 8 bits. Kilobyte again, from that point we start to count. It's 2 to the 0, 2 to the 10, 2 to the 20, and go all the way up to exabyte, which is 2 to the 16. How it is related to us. For example, for a 16-bit machine, the OS can directly access 2 to the 16 bytes, okay? And as we show here, 2 to the 16, here 2 to the 16 is in the order of magnitude of megabytes, right? Because it's between 2 to the 10th and 2 to the 20th. So it's basically 65 kilobyte, okay? And by the way, since we have 16 options, 16 bits, this is the size of IPv4 class B address space. And for those who doesn't know, is not familiar with class A, B, and C for IPv4, I recommend you go through do a quick reading in Wikipedia. It's pretty it's pretty archaic process, but it's good to know, especially with the involvement of IPv6. For 32-bit machine, the OS can directly access 2 to 32, which is what we know, what we have today. So basically 4 million, roughly to 4 million and 300, sorry, 4 billion and 300 millions, which is 4 gigabyte. And this is basically the whole IPv4 address space. And for 48 bits is we have a trillion of possibilities, which is 280 trillion, sorry. It's 13.0, and this is, and the reason that I'm calling out the 48 bits is because that this is the size of the Ethernet address space. And when we're gonna discuss the networking aspects, the networking basics, we're gonna look at the Ethernet layer as well. And for 64-bit machine, the OS can directly access 2 to 64, which is a lot, which is the maximum RAM that can be used when a particular OS is using it. And as far as I remember, XP used to have a limitation of less than 4 gigabytes, which is and this is why it couldn't scale. You couldn't use, if you use Windows XP, you couldn't use it. It didn't make any sense to use to have a computer that has a more than 4 gigabyte RAM, and obviously this problem has been solved already with Windows 7 and 8 and 10. And for 128 bits, then you see 340 billion. This is a lot of a big number, and 128 bit is important to understand because it's the IPv6 address space, and also 128 is the number of possibilities of permutations when you're encrypting with 128 bits, which is the most popular encryption length. Of course, there are some that use 256, but 128 is where it's starting to be an interesting problem. Octal and hexadecimal number system. Octal is basically and hexadecimal is basically an optimized way to look at binary number. So instead of looking at a long sequence of 1 and 0, you can use octal and hexadecimal. And and the reason that base 8 is we are calling out it as one of the helpful bases is because that 0 and 7 is something that is used in networking, and base 16 is something that is used for for computer for describing a computer a machine language. So hexadecimal is base 16. It's basically the digits 0 to 9 and A to F, which give you 16, and base 8 is from 0 to 7. How you convert? This is pretty straightforward. You take a number in base 10 and you just divided it by 2, and if you have a reminder you write 1, and if you don't have a reminder you write 0, and you stop when you have when the denominator is smaller than 2. And this is another approach on how to convert to 16 to base 16, the same thing. Okay, so now we're going to talk a little bit about how the representations of numbers in computers. So integers is a whole number with no fractional portion, so 32, 75, and it's stored as binary representation of the decimal number. 8, 16, 32, and 64 bits are used depending on integer size. Now, the reason that I'm calling out this thing is that sometimes, so when you are working with integer, and the integer is a limited number because it is holding a specific amount of memory. So what happens if you take one really big integer, which is the maximum, and then you add it with another really big integer? You get an overflow, right? So because that you don't have enough allocated data to accommodate the new number. So this is why it's important to be aware of this. And as you can see, there is a distinction between signed and unsigned integer, because when you have excuse me, a signed integer, that you need to support the minus and plus, so do you have another bit, extra bit to accommodate the sign. The number of permutations, different possible unique values that can be represented is 2 to the n, okay? And if you are talking about unsigned, this is exactly what I said, it's 2 to the n minus 1. So basically, if you have n numbers of bits, yeah. And if you want to know the range of signed values that can be stored in n bits, it's minus 2 to the n minus 1 until all the way up to 10 to the n minus 1 minus 1. Okay. And I guess that you understand that the minus 1 is supposed to accommodate the sign. And here we have an example. So let's say that we have an 8 bits, and if we want to represent 256, so 8 bits allow us to represent 256 different values. The reason it's because that it's 2 to the 8. And if you want to have an unsigned, then it's 2 to the 8 minus 1. If you want to have a signed, and then it's 2 to the 8 minus 1, 2 to the 7 minus 1, which is 128. I hope that all these things make sense. Again, I just want to call out all these things because we are going to discuss it a little bit, and I just want that we're going to have a common ground. So apologize for the CS students that are listening to this thing. Okay, now let's shift gears and talk a little bit about OSI and TCP/IP protocol. I'm not going to go through all the OSI layers, but I want you to be familiar with these concepts, and we're gonna mainly use the TCP/IP approach. So basically, we have 5 layers, the application layer, and then we have the transport layer that actually making sure that the application layer have all the context of the specific application. So for example, HTTP, it includes all the HTTP related information. If I got a packet of HTTP, I want to know what is the client who sent me this specific packet, what is the browser, and what is the user agent, what is the maybe the source IP, and all kinds of information that can help the application to make a good decision to build its logic. The transport layer, which is the TCP, is supposed to handle how the packets are delivered and processed by the application. So, for example, we are delivering a lot of packets that cannot be accommodated into a one chunk. The transport layer take care of all the sequencing. For example, it breaks the application packet into several transport packets and mark in this layer, in this specific layer, in the headers, the sequence that it should be written. And we're going to go through a real example really soon. In the next slide, I think. The third layer is the internet layer, and the internet layer is basically it's the IP. Is where it's the routing. It's the routing table. It basically says how it's supposed to help the router to where is the next hop that this packet needs to take place. And this includes, again, the IP. And then the network access is basically once that we are within a subnet, some subnetwork, we need to identify the physical endpoint to deliver the packet, which is the Ethernet address. And the physical layer is where all these packets are running through. So we can talk about, we can think about the physical layer of a coax that delivers actually the packets through a wire. It can be through a fiber optic, and it can be through the wireless, through Bluetooth or other wireless standards. Why use a protocol architecture? The reason is that data communications requires complex procedures. Sender identifies data path receivers, system negotiates, and application negotiates as well, and then translation of file format. So all these things basically supposed to help you when you are using a protocol, when you want to communicate with other components. So once you have a good understanding of the TCP/IP protocol and the protocol itself, you can standardize and be more effective. And of course, I omitted the three layers from the OSI: the session layer, the presentation layer, and the application layer. So a protocol is a mutually acceptable convention for specifying what, how, and when data is communicated. As it's basically a set of semantic and syntactic and syntactic rules that describe how to transmit data. And again, it's basically follows the same approach that I just mentioned of identifying which layer responsible to what. The protocol architecture refers to the software structure that implements the communication. Okay. Excuse me. And few more words. It takes the modular approach. It breaks tasks into subtasks. Basically, each layer in charge of a specific thing. So, for example, the TCP is for sequencing, the IP is for routing, and so on. So communication occurs between different modules on the system, on the same system, and the red arrows on the next slide, we're going to see it, just a quick peek, and this is a quick overview on how packet is moving from one place to another, and why the modular approach is more convenient. So communication occurs, as I said, between different modules on the same system. It can also between similar modules on different systems. And let's talk a little bit about it. So here we have an example of end system source, okay, that wants to send a packet into the end system destination. Okay, the canonical example is that I send HTTP GET to Google, okay, to google.com, and I'm saying, okay, Google, get google.com. So let's see what happens here. So in the application layer, which is my browser, I'm typing get in HTTP. I'm typing get google.com slash. This thing is getting wrapped into some packet. Okay, let's say that we can skip the application presentation and session. It is wrapped, and it's included in the wrapping portion. It included the HTTP command. It also includes the URI, what I want to execute, which is the slash, because I'm just executing google.com, and it also includes all kinds of good information about what is my source IP here, what is the user agent. User agent means what is the browser that I'm using, and other stuff, and what is the time that I sent the request, and other stuff. And this thing getting wrapped into some packet that getting pushed into the transport layer. The transport layer on the operating system gets the packet, add all kinds of details, for example, the sequencing things that I said. If the packet that I sent, for example, the URL was super long, that cannot fit one packet, it is going to break, the transport layer is going to break the application packet into several things, and going to mark to the destination how to read it. So if you will receive packet number 3, it will wait, and it will not just open it. It will wait, and then it will wait to number 2, it will wait to number 1. Once you have 1, 2, 3, then it will start reading. And then the network layer asks a specific question. Hey, I need to push this information into google.com. So google.com does not mean anything for me. I need to know what is the IP of google.com. So then I'm going to ask somebody to tell me what is google.com. This somebody, which is the DNS server, will return a IP, and I'm going to ask the switch, hey, do you know this IP? If he will not know, if this IP is not known to the router, all I do is basically I'm going to add this IP to the packet, and I am going to wrap it with. I'm going to ask, or I'm going to say that this is the destination IP, and I'm going to also ask who is the default gateway that I should send this packet to. And the idea behind it is that if I'm running within a subnet that I don't have the IP that can serve the request, all I need to do is just forward this information into the default gateway. And hopefully the default gateway will know something more than me. And if he doesn't know, it will be forwarded to another gateway that hopefully gonna land up on google.com, a real IP. So, and then basically the data link is getting populated with the Ethernet address of the default gateway, and all this thing is getting sent through the physical layer, which is, as I said, it can be a coax, it can be a fiber optic, it can be a wireless, whatever. And then when it hits the specific router, the physical layer going to deliver it, the data link will open the information to the network layer. The network layer will open its destination IP and will ask, I have an IP, the destination IP. Is anybody know this IP? If the router will not know what is this IP, it will close it will wrap this the new packet with the new default gateway, close the packets in the data link layer and move it to the next router on the other default gateway. It will continue to do so until it will hit a router that knows the IP of google.com. Once it hits it, it's going to go all the way up. The physical layer will open the data link, will say, okay, now I'm in the network. What is the Ethernet address? The switch will deliver the information into the specific computer. The specific computer will open it in the transport layer and wait to all the sequence of packets to be received, and hopefully open everything, and then will serve it. Once it open it, it will see that I sent get google.com/, and it will indicate it to the index, to the HTML, to the relevant HTML to be executed and returned back to the user. This is a very long explanation on how what happened when a user click on get to google.com on its browser. And here I'm going through the physical layer. I'm going through the layer, so feel free to browse over it. So the Ethernet layer is managed the transmission information across the physical link. It does the error control. It's basically identified by the MAC, the media access control address. It has MAC headers. This is the internet layer. The internet layer, which is the IP. It's unreliable and connectionless. It's also known as the routing layer. IPv4 specifically have 20 octets, 4-bit versions of number, then 32-bit source and destination, 16-bit checksum for IP headers, and 8-bit protocol, 8-bit for protocol number. So basically, what I'm trying to say here is that 4-bit, if you see here that I have 8-bit block, which is 20 octets, and 4-bit, okay, of this thing, half octet is allocated for the version. I can show what is the version that is currently supported. It's super important when the protocol relies on some of the features headers in the protocol. 32 bits are kept for storing the source and destination IP. Remember that we said here, that I need to store here the network. So sometimes I'm going to land here on the intermediate system, the routers, right? So I need to find a way to store the information for the next point. So every time that the next point will open, it will see what is the final destination. So this is why, I need to be able to store both the source and the destination. 16 bits is for checksum or for IP headers. It's just making sure that nothing went wrong on the way on the delivery. So whomever is reading this IPv4 header is basically checking the packet against this checksum and validate that it's valid header and it's not going to be corrupted. And this is the TCP, the transport layer. It's a reliable connection. It's end-to-end connection, order, error-free data stream, as I called out before. This is the structure of the TCP header. You don't need to remember that. Just be aware of that. And the application layer is, as I said, yeah, HTTP, FTP, Telnet, SSH. All these good protocols are good applications for the application layer. Okay, so here we have a basic TCP IP operation. So suppose a process at port 1 at host A wishes to send messages to process at port 2 at host B. Process at A hands a message to TCP with instruction to send it to host B on port 2. So this it's an important anecdote here. You need to understand that when you talk about TCP connection, when you debug a TCP connection problem, you need to always ask yourself, okay, who is the source host and port? Okay, so you need to have IP port in the source and in the destination. And this, so I'm going back here. So the TCP hands message to IP to send to host B. TCP might have to break the messages, as I called out, if the if the packet is too big, to hold all the message in all the packet in one TCP packet. IP hands a message to network access layer to send the router to the router X, the first hop to B. And then basically the network access layer adds in info and send the packet across the physical link. Okay, and then router X received. It's basically go through the flow that I just called out. So this is just an explanation of what is going on. Here is a practice. I want you. I don't think that this is a valid IP anymore, but let's. I'm gonna make this thing. Okay. So I have here an IP, and I'm gonna use this thing to execute trace route to this IP. This is the VM that I have. And let's see what's going on. And as you can see, what is happening here is that I have an IP, okay, and I am sending, and I want to know what is, when I sending a packet, what this packet is going through, where it's going through. And you can see that it's going through some router or networks or network.microsoft.com, and it took something like 1.9 milliseconds, and it go to other places, and then it leaves the cooperate network, and then it goes to network msn.net, which is probably the public the public IP, and essentially it landed here on somewhere. Yeah. So this is how you could see that how the packet hops and what is the time that it takes from each hop, from each router. So when we discuss this thing, every hop here is what we see here. I hope that it makes sense. So let's log in. SSH. Oops, sorry. Now what we are going to do is I'm going to log in into this into my machine, and I'm going to try to generate a TCP traffic using Telnet. So I'm going to do Telnet to google.com. You know what? So it looks like that it's locked. But sometimes, because Telnet is a very basic service, so most of the time. History, let's see, grab, as I said, let me just pick one. So I have this one. Let me log into this VM. Okay, so this is another VM, so let me use, let's do this thing, telnet on port 80. Okay, and you can see that I have here a connection port, or maybe I should do 80 here. Okay, this was the missing part. I had to specify the port ID, and this is exactly what I told you to do here. When we when we describe TCP, we always need to call out the IP and port. And basically, if I'm doing get, this is the actually HTTP command, get index.html. So let's see. Let me just close this thing. Okay, so cd var www html. So I have app.php. I have also index.html. So I can do HTML, HTTP, and this is the protocol. I think it's called, yeah, /r/n/n/n. Let's see. Okay, so I got all kinds of stuff here. And what do I see here? I see all the packets of the HTML. These are the tags that was populated by this by this ask, and this is all the return value. Okay, so you can see AngularJS forums, and this is how, let's see if it's correct. AngularJS forums, the same thing. See here, sign up. It's the same thing. So what I wanted to show you here is that how it's just to demo how a simple get works. And on the server side, so let's now take something else. We can do nick. We can do nick. Let's shut down. Let's do service. I'm gonna now build a new service that runs on this thing, so you will not see it. So we can do tail -f var www no log Apache access log. So this is now explaining all the logs. You can see the request here, but now let's do it again. So get let's see, get in app.php. This is just because I know that I have it over there. http:/r/n/n/n. Okay, so you can see here that the my Apache got a request from somebody, which is this guy. This guy is 137. And it was done here, and it was somebody asking for update HTTP, and this is basically the code. It's really busy code here. Okay, so here we can see the homework that I already published, and that's about it. Please feel free to send me a question that probably needs some more clarification about what I described here. Thank you.